Hello and welcome to this episode of Math with Martinez. We're looking at something really special today. We are going to be going through this study guide together in preparation for our Unit 2 exam on composition and inverses of functions. So let's start with some key ideas. The first is that composition is the function operation that involves inputting an algebraic expression into a function. And if we use complete sentences and precise mathematical language to explain why composition is not commutative, we might say something like this. Composition is not a commutative function operation because the order in which the two functions are composed may produce different results. Or in other words, f of g of x is not equal to g of f of x all of the time. It might sometimes be, but that is a rare case. Next, to describe the process of decomposition. To decompose a function is to express a more complicated function as the composition of two simpler functions. In other words, it's to take h of x and express it as f of g of x. And now, why would we need to restrict the domain for the inverse of a function? The domain may be restricted for the inverse of a function so that both the relation and its inverse are functions that reflect one another in that line y equals x. Very important that they are reflections in that line. And then last of all, another kind of line. What is the horizontal line test? The horizontal line test is used on a relation to determine if the inverse is a function. So these were some big key ideas that we want to be able to articulate clearly from this unit. And now let's dive into some problems where we are actually applying these key ideas. Let's begin by evaluating each function for the given value. Here we go. We want to evaluate this function f of x, which equals the input squared, with an input of x minus 3. Well, this would be to say that f of x minus 3 is the quantity x minus 3 squared because we are plugging in this into the input. So I'm going to be squaring this binomial, which means I need to take it times itself and use double distribution to expand this out. And then last of all, combine like terms. And there we have it. This is the rule that represents this function f with the input of x minus 3. Now, for example number 2, we're taking the function g of x, which is equal to 2, and evaluating it with an input of 2x plus 2. However, this function does not have a place to input anything, right? G of x is just 2. It's always 2. So g, even at an input of 2x plus 2, is still just 2. This is one of those really unique functions where for no matter what we input, the output is always the same. The output is always 2. And once again, we see that here with example number 3. H of x is equal to 32, meaning that h at no matter what we input will still just be 32. It doesn't change to 16. No, it's going to always be an output of 32. It's when graphed a horizontal line. I can actually show you this. So if we go to graphing and we just type in that function is 32, when we graph it, let me zoom to there it is. You can see there that it's just this horizontal line going through 32. So I hope that kind of helps you to visualize what we've got going on here. Okay, now let's look at this last one. We're taking the function v of x, and it is the expression 2 input squared minus 6, and we want to evaluate this function v at an input of x plus 2. So that means we're going to take 2, and in place of x, we're going to allow our input to be x plus 2. That quantity is squared. And then we will subtract 6. All right, now we need to use PEMDAS in order to simplify this. We would want to first work with our exponents and expanding that which is inside of the parentheses before multiplying the 2 in front or subtracting the 6. So then what is this going to be when we expand out using double distribution? Now that has been expanded, let's go ahead and multiply every single one of those terms by 2. And now to finish it off, we can go ahead and combine our like terms. The two 4x's, you add those up and that gives you 8x. And then we have an 8 minus a 6, which is going to be a 2. There you guys have it. Though that is going to bring us to the end of this first page where we are giving just some key ideas and evaluating. Let's look at our next page where we're going to look more at composition. We're going to, for F and G, perform each composition. We're going to write the rule for each composite function given F and G. Let's go ahead and dive in here. We want to begin by finding F of G of X. This is the same thing as writing F of G of X. So G is going to go inside of my F function. I'm really just like we were doing back over here, evaluating a function for not a number value, but an expression. What is that expression? It is the G expression rule here of 2x plus 6. So that's to take my F function, which is this quantity squared plus 2, and let that quantity, instead of just being x, be 2x plus 6. All right, we've got a binomial squared. So we're going to take 2x plus 6 and multiply it with 2x plus 6. We will distribute, double distribute. So this is 4x squared and then plus 12x plus 12x plus 36. And then that plus 2, that was out on the end. Combining like terms, we don't have anything to combine our squared term with, but we can combine our linear term and our constant term. And there you have it. This is the rule for F of G of X for that composition. All right, now let's look at G of F of X. Like we said earlier in this video, the function operation of composition is not commutative, so it is very likely that we will have a different result here when we take G of F of X. And y'all notice here, it started with G, so I have G. G of F, G of F. Some of you have done this in the reverse order, and in doing so, you have not actually answered the question. You've answered a totally different question. You do have to do the composition in the correct order. Okay, so what is the rule for F? Let's go ahead and write this in here. It's G of x squared plus 2. And so we're going to let x squared plus 2 be the input in our g function. So it's 2 and then this input plus 6. All right, so just a little bit of distribution here. And then combining our like terms. And you can see that this result is very different from what we found for f of g of x. Okay, now you might not have seen many of these, but this is a possibility where you take g of x. This is a really kind of fun and unique way to compose. This means g of x, where we're actually going to take our g function and allow the input to be the rule for g. So I'm going to take the g rule and plug it in to the g function. So our g function rule is 2 input plus 6, and I'm going to let that input be 2x plus 6. And so what does that give us? That gives us 4x plus 12 plus 6 after you distribute. And now we'll combine like terms. And there you have it. This is the rule for g of x. Now likewise, let's do so for f of x. This is the same thing as saying f of x. So we're going to take our f function, but what we're going to plug in, it's not just f of x, but it's going to be f of the input of x squared plus 2. So what does that mean we're going to do? We're going to take the input, square it, and add to it 2, because that's the rule for f, but we are going to let the input be x squared plus 2. Okay, so what does this mean? We're going to take x squared plus 2 times itself. And then very carefully, we're going to do our distribution here. Now, when we take x squared times x squared, that's x to the 4th power. And then we're going to have 2x squared plus 4. And then that plus 2 that was out on the end. All right, to finish it off here, combining like terms. There we have it. We had 2 terms that were squared, so we combined those, and then we had our 2 constants at the end, which add up to 6. That is composition, you guys. Now, let's do some decomposition. We want to find f and g such that this h function is actually the composition of f and g. Well, like I have done before, I like to first find the inside function g. I like to first find that inside function and then the outside function. So g, I'm looking for a expression that an operation is happening to. I'm seeing here that it looks like I could take x plus 2, and if that's the inside function, then f is going to be everything around that, the outside of that. 3, and then that quantity, we would call it just x, because it's before we plug in g into that spot. So it'd be 3x squared minus 4. And you don't have to put this in parentheses. It's just sometimes helpful to do that so that you can see that that is this part right here. That's this part right here where the G has been plugged into. All right. And similarly, for number 10, we want to first find our G function. So I'm noticing I have a whole expression in my denominator that's a binomial. So I think that's going to be a good thing to let be G. Then F is going to be 1 over that expression minus 3. So this would be right down here. That's where this G has been plugged in. All right, that's decomposition. Now we've got the last part of this review, which is to find the inverse of state and restricted domains. So what we would want to do here for the square root function, because I do know that a square root function does have a restricted domain, I want to go ahead and find its domain and range so that we can apply that to its inverse. The domain for this function, you could check it by graphing. Let me grab that calculator. It is the square root of x, and then outside the parentheses, minus 2. All right, so you can see here that that square root function, if we were to think about the domain, the x values, I don't have anything in the negative region. It's everything greater than 0. The domain is going to be all x's greater than or equal to 0. And the range, our y values greater than or equal to that negative 2, which again, you can see there. It has the vertex of this, that key starting point, is been shifted down from the origin sum. Okay, now let's go about finding the inverse. We'll want to replace f of x with y, and then switch x and y, and then solve for y. We do that by first adding 2 on each side, right? Doing the opposite operation. And then we need to do the opposite operation again, which is to take and square both sides. And that gives us our y isolated, just as we were trying to accomplish. And now we can write, using function notation, the rule x plus 2 squared. We also need to state what the domain would be. The domain is going to come from the range of the original. So it's going to be x's greater than or equal to negative 2. There we go. All right, now for 12. This is a rational function. Let's go ahead and find its inverse. We want to start by rewriting this as y instead of f of x. And then switch x and y. We're going to switch wherever there was an x, it's going to be a y, and wherever there was a y, it's going to be an x. Now we need to do a little bit of cross multiplying. So we would have x times the 2y plus 3 equals, well, this other side doesn't really get changed up much because the denominator over here is a 1. So when you multiply 1 times that, no change is going to occur. We'll distribute. And again, stays the same on the other side. And then we're trying to get y by itself. So we want to put all the terms of y on one side. So I'm going to add this. And I'm going to move the terms that don't have a y to the other side. So I'm going to subtract that 3x. So what we'll have is 2xy plus that 5y equals a 5 minus a 3x. Just move those terms around so that my terms of y are on one side. That's going to allow me to factor out the y as the GCF. And now I can get y by itself. It is presently multiplying with that binomial. So I will divide, which is the opposite operation. And that will leave the y isolated by itself. Let me zoom out here. This would be 5 minus 3x over 2x plus 5. My box didn't finish. There we go. Okay, so that's finding the inverse of that rational function. Let's do another. Let's do another one here. Okay, so we've got a square root function again. I know I'm going to need to restrict this domain. So let's find the domain and range here. The domain for this function is going to be affected because this minus 5 inside is going to be a horizontal translation. This is actually going to be x values greater than or equal to 5. There has been no vertical translation, so it's just going to be y values greater than or equal to 0. Now, let's find its inverse. Replace f of x with y, and then switch x and y. Do opposite operations, which is instead of square rooting, we'll need to square. And then that gives us the y minus 5 without the square root. We have undone that operation. Last thing we need to do is add 5. And that comes after the squaring. It was done after that operation, so the 5 is not squared. The 5 is just added at the end. So we have our function inverse rule of x squared plus 5. And again, remember that it is the range of the original that will determine the domain of the inverse. So it's going to be greater than or equal to 0. There we go. All right, and last one, we've got a cubic function here. Cubic functions have domain and range of all real numbers, so there's not going to be any restriction on this function's inverse domain. So we just go ahead and find the inverse. And you can check that by looking at in your notes where we discussed in Unit 1 our function families. And the cubic function had domain of all real numbers, range of all real numbers. And its inverse, which is going to be cubic, you'll see in just a moment, a cube root function, has domain and range of all real numbers as well. So here we go. Switch the y for x and x for y. Now we want to undo the more basic operations, which would be to the subtracting of 3 on each side, because we cannot undo anything inside this grouping, which is being raised to the third power. But we can undo that operation of raising to the third power by taking the third root on each side. or what we would call the cube root. So that's going to undo over here. And now last thing that we'll do is add 2 on each side. And that is after, that is, look here guys, it's after the cube root. All right, very important to show that as outside of that grouping symbol. So the inverse of this function f is the rule cube root of x minus 3, that quantity, add 2 to it. There we go. And again, there's no restricted domain for the inverse because the original function passes that horizontal line test. There's no restriction needed. It did not have a restricted domain or range, so this one will not have a restricted domain or range either. Y'all, that is it for this video where we're recapping the review. I hope that you find it really helpful just getting clarification on any questions that you had. If you still have lingering questions, take a minute to share those now. And until next time, stay fired up.